那我再跟你再多讲一点点，你们都大家都会。I cannot talk too much, right? If I talk too much, I solve your problem already. Then that won't be homework anymore. That's my homework, not your homework. Okay. Let me. Yeah. Okay. Let me explain to you. Just give you a little hint. All right. Giving a matrix called A. That phi is a n of m by n. Is a matrix, a non-singular called non-singular matrix that is phi inverse exist. Okay. And when eigenvalues of A and eigenvalues of the inverse A V are identical. This is called similarity transformations. Okay, if A is the matrix, then there exists we got unitary matrix phi transpose equal to phi inverse, such that phi transpose A transpose has the same eigenvalues of A. Okay, that's it. So I have inverse A phi. Phi inverse A phi has the same eigenvalues of A. And I also show you that if there's the matrix, then they'll have this. Now, this is the hint I give to you for your homework A. That's all. You have to think about it. You have to think. You have to use your brain a little bit more. There's just a little tricks, then you got it. Simple tricks. Okay. Any problem? Any questions? This is always exists. Doesn't matter if A is symmetric or not. That always exists. That always true. This is always true. Regardless A is symmetric or not. If A is symmetric, you can also find a dot free inverse times A times B, and that has the same eigenvalue A. So if I ask you, say, to prove you that and that eigenvalue, that means you can find some matrix such that that's true. That's all. You got to think about what kind of matrix you have to prove that equation is true. All right. Any more questions? And this later on we'll use this kind of matrix theory often in many different control methods. Okay. Any you already finished your writing? Okay, you do. And let us switch back to the note. Okay, now we discussed this called displacement feedback, and we know this displacement feedback in the title there. I wrote no energy dissipation. In other words, if I have displacement feedback, I mean I'm changing only the frequencies of the system. All right, if I change only the frequency of the system, means I don't have any despot there. If I don't have any despot there, means I don't have any energy dissipations. Okay, I will show you in the next slides. That's another feedback called acceleration feedback. My feedback is minus m1 w double dot. In other words, in this feedback, I have accelerations sensor. This is my accelerometer that measure the accelerations, and that accelerations, after I measure it, and then I multiply this computer will multiply a gain called minus m1 gain, and why I use minus m1, and I will show you because m1 here has to be positive. Now, if I sub this equation, this U equal to minus m1 w double dot, this is my force, my control force. That is a simple control force, only minus m1 times this feedback, this measurement. This is what we call direct. This is called direct. I don't do anything except just multiple this signal by a gain called m1, and put a negative sign there. And if I do that, then my cross-loop system is by sub into here, and that's I call cross-loop system. The cross-loop system originally you have force in here. If I move this fourth term, after I substitute this formula into my system equations, then I move from right-hand side to left-hand side, then I put those double dot together, then this is I call closed loop system. So there's a terminology here called closed loop system. And this closed loop system has the solution like this, and it changed the frequencies to become k over m plus m1. So my displacement feedback changed the system frequency. My acceleration feedback also changed the system frequency. Understand? And this mimic to this system. In other words, if I add m to an m1, then to this passive system, this I call passive system, this I call active system. So this passive system behave identically to as this feedback system. Their behaviors are identical. So if I do this feedback, acceleration feedback, the direct acceleration feedback, then this overall I call closed loop system. That means the whole things. Look at the whole things as one system. I call closed loop system, and this closed loop system behave identically as this called passive system. The passive system require no power, no energies. The feedback system require power and energies, right? Computer require power, sensor require power, actuator require power. But they behave exactly the same thing. Now you think about 101. If you want to change frequencies of the TMD, the 101 there, you either have to change the mass or change the spring of the 101, right? Now, that means I either add more mass to the existing mass, or I take out the spring, I replace by a new spring with a spring constant, different constant. But for active control, then you simply change the gain, M1. Then you will be able to change the system frequencies. The overall closed loop, I call it closed loop system. So displacement feedback, acceleration feedback, they change only system frequencies. And in summary. And this is all the feedback system. Very simple feedback system. So how much frequency you want to change? How much frequency you want to change? Then you can, giving the omega 1 tilt, then you can come back to compute M1, how much M1 you need to change. Now, in a passive system, the M1 always positive. Agree? The passive way. In the passive, can you have a negative mass? No. Well, the only negative mass, you can just cut your original mass to be half. Then you say, okay, I add a negative mass. But in the active, you can change M1 here to be negative. You can do that. The M1 in the feedback doesn't have to be positive, I'm saying. But you cannot change too much so that M plus M1 become negative. Then that's no good. The same thing for last slide. The passive system you can replace the spring, or you can add a spring, and that spring constant always positive. Okay, if you go back, let us go back. Okay, let's go back. This one. In a passive, K1 always positive. So when you have passive K, you add a K1 there, you increase the frequency of the system. But in the feedback, the K1 can be negative, then you can decrease the frequencies of the system. Agree? So the active has the advantages. That means your gain can be positive, can be negative. But you gotta be careful that when you change your K1, you don't change too much such that your K plus K1 become negative. And that won't be too good. Okay, now we talk about the two direct feedback. All right, and then let us look at one more feedback. That's the feedback we call direct velocity feedback. So we talk about three different feedback, the direct feedback. Now, assume we have feedback called the velocity feedback, and zeta larger than 0. All right, and that's the same thing. I have a sensor measure your velocity. Then I say, okay, my force will be U equal to minus zeta W dot. My closed system, be careful, look at this. My closed system, now I have a damping term here. In the displacement feedback and acceleration feedback, we don't have any term like this. If you think about this, if zeta is larger than 0, and there's a t here, when t large enough, this term become what? 0. Right? When t going to be very large value, then E minus zeta t divided by 2m, m is positive, zeta is positive, and minus t, if minus t is 1000, for example, this term become what? Become 0. Then your Wt become what? Become 0. Period. Your Wt becomes 0. So in the previous two slides, there's no way to make your Wt become 0. If that Wt is 0, if the 0 Wt is your goal for your system to reach, then the displacement and the acceleration feedback won't be able to reach your goal. Agree? Now, if you have this called the minus zeta W dot, if you have velocity feedback, that velocity feedback will allow you to go wherever you want the system to go. Understand? That means that whenever you have energy inside the system, this feedback, called velocity feedback, will dissipate the energy in the system. So in the direct feedback, only velocity feedback provides you the energy dissipations. There's not any other way. Displacement feedback, change frequency only. The acceleration feedback, change frequency only. The velocity feedback will dissipate energies. The change frequencies doesn't dissipate energy at all. The energy is still there, but when you oscillate, when the system is oscillating, changing the frequency of the system still oscillating, except the frequencies are different. But when I have a feedback, the velocity feedback, then the story will be different. That means we dissipate the energy of the system that allow you to move your system from one position to another position. Any questions? I show you 3 different kind of direct feedback, and also tell you all the feedback, the properties of all the different sensor measurement feedback, right? You have any questions? All right. Now, this is what we call damped frequencies. The damped frequencies have a k over m minus zeta divided by 2m and square root and take a square and take a square root of that. That's omega d. And that's the solution of the system you have. And again, the important item, the important term is this exponential form that has a negative zeta t divided by 2m, and this is the energy dissipation term. All right, and that mimic to this, mimic the real, the TND. All right, the tune mass damper. So there's a D here called damped frequency, damping. A D, TND, a tune mass damper. So velocity feedback is the damper, equivalent to damper. So you have velocity feedback here, that means you have a despot to your system. Okay? All right. Now the question is why the 101 won't use the active feedback? Why? Anybody can tell me? It seems to be active feedback makes more sense, right? Why not? Why not? Why 101 use only passive way, the passive method? The control method won't use active control method. Well, if your disturbances, that means the earthquake and the wind, if the earthquake frequencies and wind frequencies don't really change much, you don't gain much to use the active control. You can just tune your TMD for those the dominant frequencies of earthquake or strong wind. That's enough, right? So why you want to waste your money and your power, your electricity for the active control feedback? That's the trade-off. But there are in some other country they do have some active feedback for the building. Okay, now let us what we mean the total energy. This is total energy, right? We all understand. The total energy of a system equal to half mw dot square plus kw square. That's the total energy. M larger than 0 and m k larger equal to 0, right? Total energy, I think from your physics textbook. What do you mean total energy? That's the total energy, right? Now energy decay. Can energy be dissipated? If this is only m and k, T will be constant. When W dot changing small, then W will become larger. So T will be a constant. Now, when we have the velocity feedback, if you take a dot, then dt equal to m, then m dot w dot plus k w dot, then equal to w dot, take it out, m w dot plus kw. If we have the velocity feedback, then m w dot plus kw that equal to minus zeta w dot, right? If you look at this way, here this way, look at this. M w dot plus kw equal to u, that means equal to minus zeta w dot, right? So that's the formulation here. M w dot plus kw equal to minus zeta w dot. Agree? So in the next page here, the M w dot plus kw equal to minus zeta w dot times w dot means not minus zeta w dot square. If zeta larger than 0, then t dot less than 0. In other words, your energy is decaying because your energy rate is negative. That's what we call energy dissipation. Understand now? If m w dot plus kw, which is not zeta w dot, then you won't have minus zeta w dot square, because w dot square is positive and zeta is positive, minus positive times positive, and you have negative, you have minus sign in front of a positive value, and this has become negative. In other words, your energy dot, the derivative of energy, total energy, is a negative term. That means it's going down. Your T dot is negative. That means your T is getting smaller and smaller and smaller and come to the end of the energy. There's no energy at all. So to move from one position to another position, you need the energy to move from one position to another position, but by the time you reach another position, the energy has to be gone, right? If that energy is still there, it won't stay in that position at all. Agree? Any questions? So that is the direct feedback. This is the simplest control method. Means direct output feedback. That's the simplest control method. So today you learn what the control method is doing for the system, and that's it. So you have feedback.
刚刚不是说，如果没有电瓶的话，它就是能量会一直被耗在那个系统里。
Yes.
那为什么它这个还会离开？是因为有电瓶。
Yeah. If you don't have a damping, then mw dot plus kw, then that won't be, there's no w dot, no w dot here. That means if you use, for example, if you have the displacement feedback, then mw dot plus kw equal to minus k1w, right? So you, right, let me show you what happens here. Let's write down here. Okay. Then you will see what happens. Okay. Let us look at the right. Look at displacement feedback. Feedback. And T dot, right? That's dt over dt equal to dt Let's have the m x dot square plus k x squared. Then that equal to the m x dot x dot and then x double dot plus kx then x dot, right? And that equal to x dot m x double dot plus kx. Now for displacement feedback, this is equal to minus k1 x. I use w, I'm sorry, okay. Now you just change the x dot. Right, let me make to be consistent. That's w dot square and w square, right? And this is w dot, this is w dot, w double dot, and this is w dot, and this is w double dot, and this is w. All right, for displacement feedback, that equal to u equal to minus k1 w. So that means w dot equal to minus k1 w and equals minus k w and w1. Now k1. But this one, it's not always negative. If this is positive, this is negative, then this is positive. It's not decaying. It's not guaranteed decay. That's what displacement feedback. Now, for the velocity feedback, then t dot equal to minus zeta 1 w dot equal to minus zeta 1 w dot squared. And this is positive, and this is positive. So t dot is negative. T dot negative means a slope. If you have a slope, that slope is negative. That means this is my t. My slope is always negative. That means it's going down, right? This slope is always negative. Agree? The slope negative means this t is t. They won't go up because go up means the slope is positive. Agree? That's the calculus. Any questions? This is your original energy. So if I feedback minus k1 here, your original energies become like this. So this term not always less than 0. You can guarantee that. But this one is always less than 0. T dot less than 0.
老师，这一项它不会永远小于0，是不会受谁影响？
This larger than 0. This can be larger and smaller than 0, and this can be larger or smaller than 0. So multiply them together, it cannot be. There's no guarantee. If this is positive, this is negative, then positive times negative, this is positive. right? This can be positive, this can be negative, or this can be positive, or this negative, this positive. So there's no way to guarantee that is less than 0. But however, here, because this W dot is square, doesn't matter W dot is positive or negative, it's always positive, because square is always positive. Agree? Understand? So that's the energy. This is the energy. This is your original system energy. So whenever you get a feedback there, you get a feedback there, the only velocity feedback guarantee you to be that. This one no guarantee. And acceleration feedback no guarantee. Because that multiple that, they are not square. So they can be any value, any sign. Any questions? So here, in summary, only velocity feedback provides you the energy decay. Provides you a way to dissipate your original system energy already existed. Agree? So if you want to dissipate your system energy, the only way to do it is you either add a density there or you have a velocity feedback. Now, if I give you a problem, a question, say, all right, now I ask you, what direct feedback will be able to dissipate the system energy? Only one solution. Velocity feedback. Right? If I say, I give you only displacement measurement, and I ask you to do a direct feedback, then the system energies won't be dissipated. Any questions? Well, we have to understand the physics. The physics. The velocity feedback is equivalent to the densipot. That's the message I want to give to you. So when we design a controller, I mean direct feedback controller, the only way to dissipate energy is to have velocity measurement and use velocity measurement to feedback to the system. Okay? This is very useful. That's when we want to design controller later. I'm going to talk about more than just direct feedback. And you will know something you have to edit. What we have to edit. Okay, now I'm going to switch back to my slides. I want to talk about something else, which is okay. Now you understand these slides already, right? Any more questions about this? That's the way we prove the energy is dissipating. All right, now come back to 2 degree freedoms. And we talk about this already long time. And say we have an n, we have a zeta, we have k, and that's what we call mathematics. We call damping matrix and we call stiffness matrix. Now, in your homework, I just give you different coordinates. So you'll find out in your homework, you have coupling in your mass matrix. You don't have a coupling in your K matrix. But it's just the same system. I'm using a different coordinate. That's all. And so it's and then I ask you to decouple the matrix equations. And why I show this again? Just again, just show you that as long as your zeta k is positive, kc is positive, zeta c is positive, the system is always stable, and also the energy will be dissipated by this dash point, right? So, but only one requirement: k to be positive, kc to be positive, and zeta c to be positive. If those are the positive, means you have the energy dissipation in the system. That means if my M matrix is positive definite, my zeta is positive definite, my K is positive definite, then the system is dissipation system. In other words, there is something in there that will dissipate your energy. Understand? All right? And I'm going to prove to you. Matrix. This is the matrix. Energy dissipations. Total energy. The same thing. Now this is M is a matrix. This W dot is a vector. And this is vector. And this is a vector. All right? If this is the system I have, and this is total energy I got, then energy decay, I differentiate the cap T by small t, then I have a half, and to do this way, the same thing is write it out, expand it, write it out, then W dot transpose, take a W dot transpose out, then you got an M W dot plus KW. Then you get a minus W dot, zeta W dot, because M W dot plus KW, N W dot plus KW equal to a negative zeta W dot. So you sub in here, then you got a minus W dot vector T transpose times this damping matrix times W dot vector. If this zeta larger or equal to 0, then T dot less or equal to 0. Because there's negative here. So if this is semi-positive definite, then that becomes, we know that this is become the negative or equal to 0. So the energy is dissipated. So I show you the only 1 degree freedoms, and this is multiple degree freedoms, right? So multiple degree freedoms and 1 degree freedom is all identical except in the matrix terminology, we call M is positive definite. It's not just positive. In a scalar, M we call positive. In a matrix, M we call positive definite. That's all. And that definition, positive definite definition, is that a vector's transpose times that matrix and times the vector itself, then that is positive. All right. You have any question about this slide? This is nothing but just expand the concept of a scalar to the matrix. That's all. Any questions about this? So any scalar equations can be expanded or extended to the matrix case. You had a question about these equations? Now, from here now, we'll talk about matrix more because we are dealing with the multiple degree of freedoms, not just only a single degree of freedom. So we are dealing with 2 degree freedoms, 3 degree freedoms, or n degree freedoms, because control always deal with multiple degree freedoms. Any questions? Any? No? Be quiet, huh? Okay. If not, then we go, there's definition called system stabilities. All right. We know that from the previous slide, we know that if m larger than 0, zeta larger or equal than 0, k larger or equal than 0, then t dot less or equal to 0. And t is a scalar. This is matrix. That is a matrix. M is matrix. Zeta is a matrix. K is a matrix. But t dot is a scalar. And that system we call stable system. So we don't have to solve eigenvalues. We just look at m is positive definite or not, k is positive definite or not, and zeta is positive definite or not. Then we will be able to know the system is stable or not, because we look at from energy decay approach. Now that's called asymptotically stable system. Called asymptotically stable system. That means m larger than 0, zeta larger than 0, k larger or equal than 0, then t dot will be less than 0, and less than 0, this is less than 0, and this is less or equal to 0. That's the differences. So asymptotically stable system means the system energy is always going down and down and down. They are not going flat and down. It's down. Sometimes it's flat, means at that moment t dot equal to 0. T dot equal to 0 means what? T dot equal to 0 means like that. And this period, this is t dot equal to 0. Right? If t is a constant here, dt to dt equals 0, right? And this here, dt equals 0. Agree? And this in here, dt smaller than 0. And this region, dt, right? Understand? And this curve is dt less than 0. So this one is we call asymptotically stable. And in this case here, we call this stable. Any questions? Don't forget T is a scalar, it's not matrix. Okay, let us take 10 minutes break again.